Okay, welcome to the second seminar of the SERC, second drone bag seminar. Today we have the Tom Frankovich. He is the research faculty in the SERC. He has been around more than 2 decades, almost, almost 2 decades. He has been working in these systems, and so he will be presenting the talk that reduced light availability complicates SAB restoration in storage. So the thought to be the controlled by variable salinity. So, Tom?
Okay, thank you, Jay. I appreciate you inviting me. And thanks everybody for coming, and people out of BBC also. So this afternoon I'm going to talk about a water quality and SAB monitoring project that we've been conducting in the Mangrove Leaks region of Florida Bay since 2006. And during the course of that investigation, we found that reduced light availability in one of the sub-estuaries of the system complicates the efforts towards restoring SAB vegetation in there. I'm going to talk about that today. This cover slide here is an aerial photograph of the mangrove lakes. In the immediate foreground here, this is the lungs. And looking northeast, this is Terrapin Bay, and it comes all the way up into Seven Palm Lake, Monroe Lake, and Henry Lake. These are shallow brackish water lakes located within these dense mangrove areas. And I want to introduce you to the area throughout today's talk. Okay, so mangrove lakes, as I said before, were located at the northern fringe of Florida Bay, at the southern end of the Everglades. These are the mangrove.
Yeah, told you.
Thank you. These are the mangrove lakes within the square. These mangrove lakes, I said, are in the northern part of Florida Bay, above central Florida Bay. Immediately to the northeast is Taylor Slough, and these areas are particularly sensitive to upstream water levels because they respond quicker. They're shallow. They have limited connection to Florida Bay. So the water quality within these regions is highly dependent upon what goes on upstream. The C-111 Canal Project is a recent restoration effort by the South Florida Water Management, Army Corps of Engineers, and others, which they aim to increase freshwater flow into this region. And they do that by putting a coffer, some kind of dam in there to retain water within the system. Retain water that would come down through this area, but without it, that water was draining to the east and being lost from the system. So there was a loss of fresh water into the system. And historically, throughout time, these areas on the fringe of the bay became saltier, and there was a loss of vegetation. Okay, so I said historically, these mangrove lakes, these shallow lakes, were characterized by extensive benthic vegetation, submerged aquatic vegetation, SAB. In the upstream lakes, there is a green algae, Cara hornemanii, which when it's healthy and conditions are right, it can be 100% coverage, looking very dense like this. The downstream embayments are the seagrass Haliduli radii. And then there's also Rupium iridara, which is kind of an ephemeral species. It comes and goes. When it comes, it explodes. It flowers, then disappears. And you can see here, this is coming up right to the surface and having 100% coverage. This benthic vegetation in these shallow lakes is the source of food for a lot of wintering waterfowl, which visit the area starting next month and will persist through March. It's the shallow nature of these lakes that allow the ducks to access this benthic vegetation. So I said those were the historic conditions when you had extensive SAB beds in the area. But over the last century, with the diversion of fresh water, conditions in these lakes have deteriorated with decline in water quality and a loss of SAD from the system. We started early in the early 1900s with the draining of the Everglades and the Central and Southern Everglades project for flood control and other purposes. In the late 1950s, they constructed the Buttonwood Canal, which connected Coot Bay to Florida Bay, and that caused the increase of salty water into this region, which was not permitted before. Also, cuts were made between the mangrove lakes themselves, which I will soon show you, and this also allowed further saltwater intrusion. It was shortly after the construction of these canals and cuts within the lakes that Durbin Tabb described the disappearance of the SAV from these lakes. And at that time, he said that Westlake was less affected than Coot and Whitewater Bays and still represented pre-drainage conditions. The stuff I will show you today is that Westlake is one of the most affected regions presently, and the only remaining more pristine historical conditions are stuff in Seven Palm Lake. Carol McIver estimates that the salinity increase in the area caused by the diversion of fresh water was about 20 to 30 parts per thousand in this region. So there's drastic changes. These lakes were characterized during the wet season of being almost fresh, maybe very slightly saline, 5 parts per thousand. Then during the dry season, salinities would go up to mesohaline, 15 to 20 parts per thousand. Presently, these lakes are come down to 15 parts per thousand during the wet season, and during the dry season they even go hypersaline as high as 60 parts per thousand. So the salinity regimes in these lakes have changed drastically over the past 50 years. A little more history to give you an indication of how abundant SAV was historically in the area. This is a picture of the Westlake duck hunting camp, which is now the site of the Westlake restroom. And there were so many ducks down there during the 1930s feeding on the SAV that you could support a commercial hunting operation. And this is a quote from Laura Ogden's book, from Buddy Roberts, who was one of the pioneers of Homestead and the Upper Florida Keys. He says, "I seen Westlake and Coot Bay. That place feed 200 cars bumper to bumper for 2 to 3 miles there. All of them hunting. And Westlake and East Lake and Cuthbert Lake and all those lakes back there, the lungs they call on the map, it sounded just like a war." So obviously there was enough benthic vegetation to bring down the ducks, and there was enough ducks to support a commercial operation. That brings us to our study objectives. Back in 2006, Everglades National Park was interested in restoring the SAV in these areas. They were anticipating the construction of the C-111 project and the restoration of freshwater flow into the area, and they wanted to know how might the SAV communities respond to this increase in freshwater flow. And what we knew at the time, we knew that the salinities had increased in the area. We believed that this was a simple salinity story. We restore the salinity that will restore the SAV communities. The decline in the SAV communities was caused, what we believe was caused predominantly by elevated salinities that these plants could no longer tolerate. So we devised a study where we would study the water quality, link the water quality to the SAV, and then try to predict the SAV communities from these water quality parameters. So today's talk, going to divide it into basic thirds. The first 2 thirds, we're going to talk about the basic description and functioning of the mangrove lakes system, the spatial and temporal variation of water quality and SAV. Those observations were made basically on the first 3 years of data, 2006 through 2009. Based upon the results of those initial investigations, I'm going to present some of the new hypotheses that emerged from them and some recent additions to the SAV and water quality monitoring program. And then finally, we'll end up with questions and answers. This is a close-up of the Mangrove Lake study area. These are the mangrove lakes themselves. Mangrove lakes can be divided into two sub-estuaries. The eastern sub-estuary we define by the Seven Palm Lake, to Middle Lake, to Monroe Lake, Terrapin Bay, and out in Florida Bay. This lake is pretty well connected through short creeks. These creeks here are wide enough to take a 17-foot skiff through, even a 20-foot boat. The system's pretty well connected with each other. The western system, which we call the Alligator Creek Subestuary. Alligator Creek Subestuary is West Lake, Cuthbert Lake, both of them connected to Long Lake, eventually through a long tenuous creek, Mangrove Creek, into the lungs, and then another very long, tenuous creek through Alligator Creek and added to Garfield Lake. Numbers are the sampling sites where we measure water quality parameters and SAB parameters. The sites in purple here are recent new additions in the Cuthbert Lake. We originally weren't permitted to go in there. The letters are areas where we have continuous water sondes, where we measure temperature, salinity, and water level. We measure the SAB community composition quarterly. About every 3 months we get in there, historical, put quadrats down, measure the community composition, collect sediment and tissue samples. Water quality monitoring we do approximately every month. We take spot measurements of temperature, salinity, water depth, Secchi depth in the past. Now it's more direct measurements of light attenuation, nutrients, total nitrogen, total phosphorus, chlorophyll layer for phytoplankton, turbidity, and CDOM, recent additions. And I already mentioned the sondes. The photograph up top here is a sonde station. Also gives you an indication of what the water looks like. This is water from West Lake. Very turbid, very nutrient rich, and also very phytoplankton rich with very low visibility. Jumping right to our results. This here is a cluster analysis of the SAD community composition data. And from that cluster analysis, we identify 3 community groups. One group characterized by the green algae Chara, another group characterized by Haliduli, and a third group where there's basically very little to zero vegetation. A little closer look within those each community groups. The Haliduli group is about 25% cover, average Haliduli, 6% Phytophthora, which is this little epiphytic algae down here. And then a lot of it you can see here is bare sediment. The Chara group, mean 33% Chara, low SAB group, almost entirely bare sediment. So these three distinctive community groups. These community groups are aligned along spatial gradients, with the Haliduli seagrasses down along the northern embayments where the main part of Florida Bay is. The Haliduli are all up in the upstream lakes, and the low group, the low group is confined to the western Alligator Creek subestuary, all but that is within the Chara group. Looking at the physical characteristics within each of those community groups. These are box and whiskers plots. And then we have Haliduli group, Chara group, and the low SAB group, plotted against salinity, sediment depth, and light availability. And what I want you to take away from this graph here is that these community groups have different characteristic environmental characteristics. So the Haliduli group is characterized by the highest salinity, sediment depth, and also the highest light availability. Chara is characterized by lower salinity and sediment depth and high light availability. And the low SAV group was characterized by the lowest light availability.
Is your sediment depth to fuel?
Sediment depth to bedrock, yeah,
Yeah.
the right to bedrock. One of the aims of our project for the Park Service was to be able to predict how these communities may change when fresh water was delivered into the area. In order to do that, we have to come up with a model, a successful model that is able to predict community groups from the environmental data. So we used a discriminant function model to be able to predict these community groups. We found that just using salinity, we were able to do a very good job of predicting these community groups. In fact, 78% accuracy with just salinity, but we could reproduce those community groups. We had sediment depth and light availability to that model, and we increased that accuracy to 90%. By community group, we were able to correctly identify 100% of the Hallelujah sites, almost 90% of the Cara sites, and 3/4 of the low SAV sites. Looking further at the discriminant function model, this here is an ordination plot of the SAV community composition data. Along the X and Y axis are the discriminant functions, and then the letters inside are the site scores. And these are the site scores, how they rank according to discriminant functions. And these site scores are coded according to their community group. And in this first graph here on the left, they are coded to the actual groups identified. On the graph on the right shows coding according to the predicted group. First thing you should take away is that the model did an excellent job of predicting. You see very little difference between the predicted and the actual coding of these two figures. Also notice that the community groups are well separated within these plots. That the low group over here, within the Cara group on the end, separated from the Hallelujah group. Outside of these graphs are the correlations with the environmental variables. And we see that as we progress from the low vegetated sites to the Hallelujah sites, we increase light availability, increase sediment depth, and increase salinity. Looking further in, drilling deeper, we look at how the individual water quality predictors are able to distinguish individual pairs of these groups. So specifically, how was the low group distinguished from the Cara group? How was the Cara group distinguished from the Hallelujah group? What specific parameters were most important? And this table here, showing the results of linear contrast analysis, indicates that slight salinity, light availability, and sediment depth distinguish Cara from Hallelujah. Uniquely, light availability is most important in separating the low SAV group from all the others. So, we see that light availability is very important. Light availability is what distinguishes the lack of vegetation in these upstream lakes from areas where we have Cara coverage. So, next question would be, okay, well, what's causing this decrease in let's say, the low SAV? So we look at, we know it's light availability. So proxy of light availability would be Secchi depth, which is water transparency. So as you increase Secchi depth, you increase water transparency, increase light availability. And you plot the Secchi depth versus chlorophyll A, the phytoplankton concentration, we get a very strong negative relationship, clearly showing that we get decreased light availability at greater phytoplankton concentrations. We also note here we have a clear separation between the two systems. The eastern McCormick Creek subestuary, which is characterized by clear water, abundant SAV, has much lower light availability, much higher light availability, much lower phytoplankton abundances than that in the Alligator Creek subestuary. So we have two subestuaries sitting right smack next to each other with two drastically different water quality regimes. Delving further. Okay, so we see a relationship between light availability and phytoplankton. What's driving the phytoplankton? Well, it's phosphorus availability that's driving the phytoplankton. We have a big difference between the two systems, between water column phosphorus levels. In the western Alligator Creek subestuary, we have much higher phosphorus levels related with lower chlorophyll, with higher chlorophyll. And in the eastern system, we have lower phytoplankton, lower total phosphorus. So to summarize the results from our spatial analyses. One, we were successfully able to reproduce those community groups just from the environmental data using the discriminant function model. We also found that there's the two subestuaries within the system characterized by drastically different water quality regimes. One regime characterized by high phytoplankton concentrations, high nutrients, low light availability. The adjacent system characterized by just completely the opposite. So next step would be look at how this system reacts temporally. What's the temporal variation? So these are some plots here focusing just on the CARA communities because this is the area where we're noticing SAD loss. This graph here shows a time series of CARA cover from 2006 through 2009 in both estuaries, McCormick Creek in the east and Alligator Creek in the west. And we find that, in fact, in McCormick Creek, where we have much higher light availabilities, lower nutrient or phytoplankton, we have higher CARA coverage than in Alligator Creek. As for seasonality, we only noted seasonality in the Alligator Creek system. Seasonality, I mean wet versus dry differences. In McCormick Creek, we definitely had a temporal trend of decreasing coverage. That was more of an interannual trend and not seasonal. Looking further on some of our environmental variables, this is total phosphorus. Again, total phosphorus much higher in the western Alligator Creek than in McCormick Creek. There's little interannual or seasonal, repeatable seasonal variability. It's variable month to month, but there's no repeatable patterns. Chlorophyll, again, this shows the pronounced differences in the Alligator Creek subestuary, much higher chlorophyll concentrations than in the adjacent east subestuary system in Alligator Creek. Interannual variability, but no repeatable seasonal variability. Temperature, as you expect, higher summer, lower than that. That's nothing exciting. Salinity shows similar patterns in each system, but much larger amplitude in Seven Palm than in Westlake. You see a slow ramp up of salinity during the dry season, associated with a rapid decline during the onset of the wet season until it finally ends, and that starts to climb again. This, according to our analysis, the way we defined wet and dry seasons, there was no wet versus dry season differences in salinity because the peak and the shallow and peak salinities are located at the transitions between the wet and dry seasons in our area. Sorry, do you have a question?
Is that because one lake is more susceptible to excision from?
Yes, exactly. That's a good question. The question was, what is the greater amplitude due to the fact that the Seven Palm Lake system, Seven Palm Lake is that eastern McCormick Creek system, and it is because it is better connected to Florida Bay. So what you're seeing there is just it's a greater exchange with Florida Bay waters than the West Lake system.
There's certain increase in trend salinity in both.
Pardon me?
You have the seasonality or whatever,
Yes.
that fluctuation, but you have a trend which is increasing in both.
Yes, it's increasing both over those years. Yes, so
That's
there's an
everywhere.
annual trend.
That's everywhere.
We have a seasonal pattern in the water level, and this is important for SAB in the region. The water level declines during the dry season and then increases during the wet season. The patterns are quite similar between the two systems. Note that there's much greater variation again in the Southern Palm system, and again, that's because of the greater connection. So as the winds blow out of the south or north, you get it almost immediate response in water level in the Southern Palm system. You get a much dampened response.
So
in the
what's the
Westlake
water
system.
level relative to?
This water level is the mean water level. So it's 0, so that's a relative water level. So we took the,
Okay, so it's never dry. They're lakes.
right,
Okay, that's not
those are never
below.
dry. Oh,
Okay.
yeah, it's not absolute, that a relative water level, that 0 is the mean.
Okay.
So, one of our goals in our tempo analysis was to look at correlations with environmental variables. With the spot measurements, we employed wet versus dry season differences. With the continuous SON data, we performed some correlation analysis. This table here are the results of the light availability analysis. And here we have Alligator Creek, wet versus dry, McCormick Creek, wet versus dry. KD is the light attenuation coefficient. The higher the light attenuation coefficient means that less light is transmitted to the bottom. Mean water depth between wet and dry season in both systems. Here, McCormick Creek is a little deeper at our study sites. Percentage light at the bottom, and finally our total bottom insulation, which is estimated from equation taking into account the light attenuation coefficient, the water depth, and what's not on here is the incident insulation. But what I'd like to note here is that in the Alligator Creek subsystem, the light availability was 5 times greater. So we have 5 times greater light availability in the dry season, in the wintertime, and that's associated with higher Cara abundances during that time in that system. Our correlations using our continuous SON data, we only found correlations, significant correlations in the McCormick Creek subestuary, where the Cara cover was negatively correlated with salinity and negatively correlated with depth. Get into that in a little bit. So, summarize the results of these analyses. We noticed variability in both SAD and the water quality parameters. Only in the Alligator Subcreek estuary did we notice a repeatable seasonal pattern with Cara cover. There was no seasonal pattern in McCormick Creek subestuary. The greater Cara coverage in the Alligator Creek subestuary was associated with lower water temperatures, lower water levels, higher aquatic insulation. In contrast, the SAV communities in McCormick Creek did not exhibit the wet versus dry season seasonality, and the Cara cover was negatively correlated with depth and salinity. This suggests that the poor light availability in the Alligator Creek subestuary was more important than salinity in permitting the Cara to grow. Once you had enough light availability in the systems, then the Cara could respond to changes in salinity, as we might expect. So at the end of those first 3 years and these temporal and spatial analysis, we realized there was a bunch of unanswered questions. So we knew that light was important, and we definitely saw that phytoplankton was responsible for the spatial differences between the two subestuaries. But temporally, we had some indication that light was important in the Alligator Creek subestuary, but it was not necessarily that the temporal variation was not driven by variations in chlorophyll, but it had something else to do that was associated with water levels. And 2 of those things could be the water level itself, and another thing could possibly be CDOM concentration. So we knew that we needed to start measuring CDOM in our next efforts. We also saw that these phytoplankton concentrations causing these decreased poor water quality in Alligator Creek was driven by phosphorus, and there was almost much less phosphorus in the eastern system, but we needed to know where are these nutrients coming from. We had no idea what were causing the drastic differences between nutrient availability between 2 adjacent systems. We had no indication as to why things may be different, so we realized that new data may be required. And we started to measure turbidity, started to measure trypton, we started to directly measure light attenuation. We also, importantly, expanded our sampling into Cuthbert Lake. I'll show you where that is very shortly. And we initiated sediment, plant, tissue nutrient sampling to try and identify nutrient source pools. So Cuthbert Lake. Cuthbert Lake wasn't part of the original sampling program because we were not allowed access in there. This is an area of a bird rookery, so it's off limits to not only the public, but even to researchers who get special permission to get in there. Cuthbert Lake lies right smack in between our two study areas, our Alligator Creek subestuary in the west, which had the rotary poor water quality, and our McCormick Creek subestuary, which had the abundant light, abundant chara, low phytoplankton. So the question was, hey, is this missing link? Would we see just a general transition of water quality conditions from West Lake over to Seven Palm? This Cuthbert Lake kind of had conditions in between them. But we had no idea because we never been in there. So eventually we got permission to go in there. We initiated sampling and we found out one that has a rocky karstic bottom, very similar to Seven Palm, as opposed to West Lake, which has a thin veneer of sediments throughout. Sediments in the other systems are located just on the periphery, but in West Lake, you got decent sediments even in the middle. The sediments here are also different from the other areas. They're very flocculent, has a floc layer of about 10 to 20 centimeters, almost like liquid, very easily stirred up, iron rich. The sediments would stain our sampling equipment red, indicating the presence of iron. It's, as I said, it's the site of a significant bird rookery, so we speculate, maybe this is a source of nutrients, possibly into that Alligator Creek subestuary. Could this be the reason for the differences in water quality? So, we started collecting data, and the first thing we noticed is that the water quality was horrible. Like the Alligator Creek subestuary, the West Lake system, but it was even higher. We think about Alligator Creek being, double the concentrations of that in McCormick Creek. We find that Cuthbert is another doubling. These are huge concentrations of water column total phosphorus, 4 to 5 micromolar, tremendous amount of phosphorus. Phytoplankton, as you expect, responding to that abundant phosphorus. Phytoplankton levels are huge. These are mean levels, consistent levels of 30 micrograms per liter. In Florida Bay, you consider the major phytoplankton blooms being about 15 micrograms per liter. Just the end of this past dry season, we measured phytoplankton concentrations, chlorophyll A in Cuthbert Lake at 130 micrograms per liter. This is comparable to what you see in some of the extremely polluted freshwater lakes, Lake Togo and up north. Very, very high phytoplankton concentrations. Sediment phosphorus blows everything else out of the water. Very high phosphorus levels in sediments. SAV cover, as you'd expect, low. Other parameters, remember we started measuring, we talked about CDOM, we speculated that CDOM might be important because we noted a temporal correlation with water levels with our SAV chara coverage in the western subestuary, the Alligator Creek subestuary. Associated with low and high water levels are CDOM. CDOM is a significant light attenuator, and as we expected to find, CDOM is highest in the wet season and then decreases during the dry season, and again you have another spike in the wet season. And this could be important in explaining some of the temporal variation in our chara populations in the western subestuary. Turbidity. Turbidity is another important light attenuation component. For most of the system, turbidity is pretty stable throughout the year, except in Cuthbert, where it's highest in the wintertime. Again, Cuthbert has those very flocculent, very easily stirred up sediments. It's no surprise that turbidity peaks in the wintertime. Henry, your Florida Bay data shows the same thing. That's when wind speeds are highest. So if we use turbidity to try and explain some of our temporal variation in our chara populations, it doesn't support it because our Cara populations and our seasonality was highest in the wintertime. That's exactly when turbidity is highest. So it lends support that something to do with water level and CDOMs are responsible for some of the temporal variation. That summarizes the temporal and spatial factors, and that leads us to 4 hypotheses. Because why do these adjacent subestuaries, which are right smack next to each other, exhibit such differences in water quality conditions? And these water quality conditions translate up the food chain, up to decreased carp populations, decreased ducks. What is it about these systems that is causing the market observed differences? We're going to investigate 4 hypotheses. 1, concerning the geography of the area. 2nd, hurricanes, tropical storms. 3rd, bird island effects. And then finally, different groundwater sources of nutrients. Is that a possibility? Going to geography. I explained a little bit about this before. Eastern system, well connected to Florida Bay. We see very similar water column concentrations throughout the whole system. Basically, the whole system reacts very similarly to each, the sites within react very similar to each other. In the Westlake system, we get the differences are greater within each basin. The connection between Westlake and these lakes with each other is very tenuous. The creeks are very long, very shallow, very narrow. In between these creeks are these settling ponds, what I call settling ponds. So any particulates which may come into the system through the creeks are going to come in and maintain themselves up in the water column in the high velocity creeks, come down to these settling ponds, get settled out. So by the time any water carrying particulates comes into the system, it's already dropped out. Also, think about what would happen, or what does happen during tropical storms, hurricanes, when you have a storm surge. These lakes are separated from Florida Bay by Buttonwood Embankment, which is approximately 3 feet in elevation. So Hurricane Wilma was about 5-foot storm surge. Donna had a much higher storm surge. As that storm surge comes in, obviously all that water coming in is very, very stirred up, full of particulates, floods the system. The particulates, as that water recedes, will settle out. The water in the 7 Palm system is able to flush out much faster because of the greater connection. The water in the Alligator Creek subestuary settles out much more slowly because the connection is not as great. So there's a lot more trapping of sediments within the system here. We know that there are reports showing that Hurricane Donna dumped a lot of sediments into the Westlake system. And it was localized. It was mostly in the central to western part of Westlake. No sediments made it over into the Corner Creek subestuary. A little further information on that. That mud, which was deposited inland from Hurricane Donna, was 3 to 10 centimeters thick. Recent analysis on Hurricane Wilma mud, which we assume was very similar to the Hurricane Donna mud, found that that's Edward Castaneda, you know he works on our LTR, found the phosphorus inputs from those nutrient-rich sediments were fertilizing these interior areas. The marine sediments are actually higher in nutrients, so when these marine sediments get transported into the system, you have a input of nutrients into the system. So we speculate, is it possible that this differences in geography and in these storm sediment transport of nutrient-rich sediments are fueling these, creating these higher nutrient conditions in the area and fueling these blooms? Possibly. Another hypothesis was the Bird Island. Cuthbert Creek is connected to that western Alligator Creek subestuary. It's also the center of the very poor water quality, the highest nutrient concentrations, highest phytoplankton. It's also the site of a significant bird rookery, which was much greater in the past. We know that these bird rookeries and bird nests are sites where nutrients are concentrated. So birds are feeding all over the place, coming into roosted nests, defecating all of that nutrient-rich guano is in the system. That combined with the geography of the limited circulation within the system tends to trap these systems, to trap nutrients within that Alligator Creek subestuary. Groundwater, our last hypothesis. I'm going to revisit the river of sand. I don't know if you recall the river of sand. That was a Larry Brand theory where he speculated that there was a connection from high nutrient groundwater sources elevating from upstream agriculture, eventually coming down all the way to Florida Bay and then causing phytoplankton blooms and killing the Florida Bay seagrasses. Well, that theory fell apart because the seagrass die-off in Florida Bay had nothing to do with nutrients or eutrophication. The die-off occurred in a crystal clear water column with very little nutrients. But we need to revisit his river of sand hypothesis because he based his river of sand hypothesis on Cunningham's work where he shows these phosphorate deposits in the Everglades and underneath Florida Bay. This graph here is his figure showing the proximity of these phosphorite deposits to the surface. And the shading indicates how far below the surface it is. And it shows that where the Alligator Creek subestuary, our western area of our mangrove lake study area, is also coincident with the area where these phosphorite deposits are located closer to the surface. So we speculate, is it possible that with saltwater intrusion into these areas caused by decreased freshwater flow, that the saltwater is intruding into the area and then traversing through these phosphorite deposits, bringing relatively nutrient-rich groundwater into the system? And if these maps are accurate, is it possible that we have a differential concentrations of nutrient groundwater coming into the system with greater nutrient groundwater coming into the western Alligator Creek versus the east? We don't know, but that's the start of a new project. I know Renee is heading that, and we hope to come up with an answer. And again, that's the reason that occurs is something that Steve Davis spent a lot of time on. Florida Bay is an upside-down estuary. During the dry season, when water levels drop in the Everglades, we actually get marine water intrusion into the Everglades, so we actually get water transported up into the Everglades. And because the marine water is actually higher in phosphorus concentrations than the Everglades water, we actually get input of phosphorus into the system during these times. So, with restoration, if we want to restore vegetation in the area, we know that a lot of the CARA vegetation has to do with favorable salinity conditions. That drives a lot of the spatial variation, but we find that a lot of the temporal variation has to do with differences in water quality, particularly water availability, and those high nutrients. We can solve both of those problems, we believe, with the same strategy. Increasing fresh water will push out both the salt water, creating more favorable salinity for CARA. It will also push out the more relatively nutrient-rich water and alleviate some of that nutrient problem and alleviate some of those phytoplankton.
Tom, do you think that model, that simple model,
Pardon me, that single.
model of a lower P from the Everglades water and higher from the sea explain what we see in nutrients in all those areas?
In these areas, well, what we have to do there, it would have to be differential. If we figure it's coming in there, you would have to have lower phosphorus concentrations coming into the east than the west.
What happens is that within the mangrove forest, you have higher concentrations of phosphorus than those that you have in the seawater.
Right.
And so that model doesn't work.
If it's trapped,
That's a mixing model.
a mix.
Yeah, you mix seawater with fresh water. So if that's true, then you should have intermediate P concentrations within the mangrove forest. And you don't. So you need another source.
I have a quick question for both of you. This is Bill at BBC. But Henry, if that was true, you have lots of, those are TP, right, Frank, or SRP?
Yes, yeah, those are TP.
Those are TP, so if you have lots of DOM, your TP is gonna be shooting up, and it's about flushing times of those lakes, correct?
Yes, flushing time is extremely important.
Yeah, I'm pointing out to the spatial distribution of TP concentration, disregarding the you know what species are they, if they are associated or not to organic matter. So we have something that cannot be explained just by a mixing model like this.
Yeah, so Henry, there's this other source of fresh water, and that's the groundwater.
She has been working on that. That's one of them. But soils are too.
Yeah, exactly.
Soil. The collapse of pit bogs due to lower freshwater input, plus higher inputs of marine waters that cause all this soil destruction and pit collapse. Is perhaps, I don't know, it's perhaps the source of a larger nutrient concentration.
Right, okay, but I can see that. One thing missing from that would be, you know, why hasn't Florida Bay shown those blooms along the immediate area? If you feel that the phosphorus is getting remobilized because of the loss of the peak, it would expand both north and south. In fact, more prevalently, it would flow to the south.
Yeah, but you see that most of it look like the resin steins are very large. And whenever you have something going all the way down to Florida Bay, that's going to strip out of a lot of nutrients and sediments and everything through the mangrove forest. You are just mentioning that. I don't know, it's just, I never liked that simple model.
Your sediment TP model, or your sediment TP idea would be 1,200 micrograms per gram. I mean, you could actually, just by mass balance, see what effect that a hurricane distribution would have on that. Now, those are huge numbers. So, I mean, if you didn't get, you know, a lot of sediment in a small event, you know, those are big numbers. So you can see kind of the magnitude of what effect you would have to have. It was just simple mixing. I mean, we would have to dump everything in one small area to get like an eightfold increase.
Yeah, I said, yeah, I present, you know, these hypotheses are just hypotheses, they're definitely not conclusions, there's things that we are looking at.
And there's not really a source for sediment phosphorus from storms getting into Cuthbert. There's no way for water to flow over it, so can't really explain those high phosphorus concentrations in Cuthbert with storm overload.
Right, exactly.
More than one thing, right? More
Yes.
than one.
Well, that actually brings us to the end of the talk. We really only talked today really about those first 3 years of data. Don't have enough time to talk about the rest, but we do have some exciting things happening right now. You know, the C-111 spreader canal project, actually the spreader part's not initiated, but the retention part of it has. That started last fall, and coincidentally, we have noted dramatic changes in the system already happening. I said coincidentally at the same time. You know, we'll stick our neck out and say it's from that. But the consistent phytoplankton blooms that never disappeared for 6 years, and that went high. This last sampling went down to just about 0. The SAV coverage is 100% in Westlake. So the differences we described here between the two subestuaries do not exist anymore. I mean, right at this present time, the chlorophyll levels are down to 0. We haven't got the nutrient data back from our most recent thing, but the change is dramatic. The change actually started last winter. We started noticing also some more ducks. So it's a very exciting time, and if it holds, it'll indicate that this project is working.
Yeah, but when Jenny and I worked in there decades ago in Westlake, there was a whole lot of caribou. So, and that was without the C-111 retentions.
Yep. It's different. You know, even if we just were to make our conclusions based upon those first 3 years of data, without making it to what is presently year 7, you know, we'd miss a lot of the processes that occur over a long time series and make wrong conclusions. Yes.
I would just like to note that when that C-111 project came online last year, it was coincident with the end of our 6-year drought. So I think it's going to be really hard to discern how much of the effect is from the restoration versus the ending of the drought and all this rains.
Yeah, I haven't looked at that data. I've talked with Pete Frez at Audubon, who's been analyzing data, and he said that this last year he noticed similar things with his SAV, huge amounts. But he said that the water levels and the water levels and the flows and the precipitation were indicative of higher years, but we're not the highest. So he was attributing this especially to the decrease in salinities was dramatic. And that's something we've also didn't mention that recently, but the salinities have also come down to very, very low levels and have persisted for a longer period of time than they have in the past. So there's time when these lakes would go saline, the hypersaline did not occur last season.
They think it's
And
more
probably will not occur this season either.
They think more complicated. So what Renee was saying is that now we have a very, very wet year, abnormally wet. So after a very dry period, now we go into a wetter one.
Yeah, you know, we'll see exactly how normally wet that is. It's definitely wetter. So PFRES's indication so far is that it's not out of line with what's happened in the recent past, in the last decade. Yes, Jenny.
How big is the rookery in Cuthbert Bay, and how long has it been there?
Okay, I can answer both those questions. A little bit. For the size, okay, that looks huge. It's not.
So that's it, what we saw there?
It is amazing. I heard about this famous Cuthbert Rookery, and I've never been in there before. And then I go in there, and God, you can go around it and with a little John boat in less than 5 minutes. You go, God, this is it. And you think, how can this little tiny place, you know, we think about our theory of, you know, nutrient input in the area. How can this tiny place give it to the whole area? So it's tiny. How many birds? Thousands. I don't know the exact number, but there were a lot more in the past. That's I recall when that was taken. Obviously, when
But less dense rookeries of the same size have noticeable impacts on phosphorus availability in Florida Bay with much greater flushing. So, you know, you go hundreds of meters from Duck Key and see the effect of the rookery. So you can't discount it out of hand because of the really low flushing rate.
no, you know, it didn't quantify. It didn't, you know, all these things need nutrient budgets.
That's one thing you said.
Yes.
How deep is Cuthbert?
All these lakes are pretty shallow. The deepest part of Cuthbert may be a meter and a half, but I've only gone down and probed in the center part once, and so the water quality is poor. There's no visibility in these lakes. They're full of alligators.
You usually swim into the sediment.
Yeah,
Halfway into the
you
sediment.
kind of bump into the sediment, you bump into the rocks in the case of Cuthbert. So we need seeing at the karst bottom there, the transition from West Lake over to Seven Palm Lake. Any other questions? Yes, Steve.
Yeah, and thinking about your flushing idea, and also considering legacy of bird use, to some extent you could say that, well, and you suggested that when you go from west to east, you perhaps experience more flushing through these lakes. You could also think that, yes, since the system's been deprived of fresh water, those areas in the west have seen perhaps reduced flushing for a longer period of time than those in the east. So not only do they flush less due to the geomorphology of the basins and the connections between those basins, but they've also seen reduced freshwater for a longer period of time. You could assume maybe with the constriction of Taylor Slough
Sure, yeah.
over the past 50 or more years. So I guess what I'm saying is that your hypotheses could get, I mean, they're not mutually exclusive the way you presented them necessarily, but I can also see how you've got really interesting space-time aspects to consider as well.
Right, the geography is an overarching, it would affect all those nutrient inputs. The three hypotheses concern nutrient inputs, and then the fourth hypothesis was just geography, but geography impacts the other three nutrient additions, yes.
So Westlake is the only one that has kind of anthropogenic inputs at the upper end, right?
How do you define?
Well, so you mentioned where the outhouse was or something
Oh.
like that.
Okay,
So how does waste disposal happen?
that's pumped out, yeah, no, that doesn't go into the lake, that was pumped out, but yeah, sure, when the duck hunting camp was there was pumped out. But, the park facility is pumped out, I don't think there's any recent nutrient addition in the system. But, important point is, and that's in all these systems, once the nutrient gets in there, particularly phosphorus, it's so valuable, it's so nutrient limiting, once it's in the system, it's gonna be very, very difficult, in fact, probably impossible to get out, probably just have to be buried. So the historical nutrient inputs into the system, particularly phosphorus, are probably legacy things which are gonna persist in the future. Yes?
I had another thought when you were presenting, you mentioned wind, and you think about the orientation of some of these lakes and the positioning of sites that don't support submerged aquatic vegetation. Have you seen evidence of fetch effect with prevailing
I
winds or-
specifically looked at that, because that's a common variable that they look at with carrot communities in these shallow lakes, particularly in Europe. They've done a lot of stuff looking at fetch, and it doesn't fit here. Some of our highest areas are on the most wind-oriented areas. Not exactly, but definitely a lot of the quiescent areas will definitely have carrot in it. Yeah, but conversely, not all of the high energy areas are lacking Cara. So there's a lot of high energy areas on the windward edge, that catches all the energy but has a lot of Cara.
I was
So
also
it
thinking
doesn't
with
explain our
sediment
Cara.
thickness also,
Our sediments,
with sediment thickness.
sediment thickness. Now the only place we saw some sediments kicked up and turbidity was in Cuthbert, where you had the flocculent sediment. So I mean the density of the sediments at the other sites is sufficient enough to keep it down most of the time. So yeah, turbidity, it's out there, but it doesn't seem to be causing any of our temporal or spatial variation. Yes.
I have a question about the first part of your talk, when you were doing was it a principal components analysis?
That was discriminant function analysis.
Okay. Did you include total phosphorus concentrations in that analysis?
Yes, I believe I did. I can be sure. I can check it out for you. In fact, I have copies of the papers that detail the results of these investigations and the fact sheets of them. I can look that up. I'm pretty sure that we included all the environmental variables in there. Anybody from BBC? Anybody still there?
We're still here.
All right. I guess it's just not up on the screen.
Budget?
Okay.
Very good.